So now what we want to do is to introduce the idea of population inversion. We need to obviously explain what we mean by that. But essentially, we've seen that to get more stimulated emission than absorption, we need more atoms in level 2 than in level 1. So the population of level 2 must be bigger than the population in level 1. We need more atoms up here, and fewer atoms down here, so that we can get the stimulated emission as being the main process that's happening inside the laser material. If we don't do anything we have a box of atoms that's going to comprise of the laser material. If we don't do anything, if we just leave it to reach thermodynamic equilibrium, this will not necessarily be the case. In fact, it almost certainly is not going to be the case, because as the number of atoms in level 2 relax back down into level 1, then you're going to have more atoms in level 1 than in level 2. And we saw that when we looked at the Boltzmann statistics. We saw that for, again, I think it was for Ruby, that at room temperature under thermodynamic equilibrium, for every one atom that we had in level 2, we had 10 to the 30 atoms in level 1. Okay, so under thermodynamic equilibrium, the population is normally that N1 will be much bigger than N2, and that relationship will be given by the Boltzmann factor here, a negative exponential. And so N1 will be bigger than N2, and that's normal population distribution. What we need to do is we need to find a way of making the number of atoms here bigger than the number of atoms in level 1. So more atoms in level 2 than in level 1. For that we need negative absorption, in other words gain, and that means that the populations, instead of being under normal equilibrium, will be inverted. In other words, we have lots of atoms in level 2 and very few atoms in level 1. So this is inverted from the normal situation that we would have at equilibrium. So population inversion means that we have a system which is very far from thermodynamic equilibrium. Okay. Lasers don't work if they're in thermodynamic equilibrium. We need to have more atoms up in level 2 compared to the number of atoms in level 1. The point where we have the same number of atoms in level 1 and level 2, this case where the absorption coefficient or the gain coefficient is equal to 0, is referred to the inversion threshold. So again, you'll see this in some textbooks. If it's talking about the threshold of inversion or the inversion threshold, it just means that you're just at the point where the stimulated emission is starting to be bigger than the amount of absorption that you're getting. Okay, so the stimulated emission are very similar to the rates of the absorption, and then you go above threshold, then you're getting more stimulated emission, you're getting gain in the material. As we increase the population of the upper level, as we increase the inversion, then we'll get the emission processes outnumbering the absorption. We get the incident field, the starting signal, if you like, experiences coherent gain, and we end up with a nice clean laser beam coming out the end of the box as it passes on. And remember again that the coherence is the key thing here. All the photons in the laser beam are coherent. In order to do that, in order to move the atoms up into level 2 from level 1, we need to provide some sort of energy source. We need to put energy into the system to move it from level 1 up into level 2. And we can think of this as being a bit like a bucket of water, so that this is with the well, this is where all the water is, and this level 2 level 2 is like our bucket, but our bucket has a hole in the middle. Oops, that's a big hole, sorry. Our bucket has a little hole in the middle. So that as we pump atoms up into level 2, if we don't do anything, then some of them will fall back down into level 1 spontaneously. In order to get more atoms in level 2 than in level 1, we need to put in lots of energy, because we need to get at least half of all the atoms up into level 2. Okay, so this pumping process, you talk about pumping the laser or using different types of pump energy or a pump source, is to populate the upper laser level. In gas lasers, that might be from the current being passed through the gas, as in a neon tube, and you're getting inelastic collisions with the electrons. The electrons are then transferring energy, moving the atoms or ions up into higher energy states, and then when they relax back down, they give out our spontaneous emission and hopefully stimulated emission. For solid state lasers or solid lasers, not laser diodes, usually these are optically pumped. In other words, we use maybe a laser diode as our excitation source, our pump source, or we could use a flash lamp, or lots of other options. But usually there's it's some sort of optical process for solid state lasers in the kind of near infrared and the infrared. In real laser systems, we have more than 2 energy levels. As we've already seen, if you've only got 2 energy levels, you can't really get the laser to work, because getting more atoms in level 2 than level 1 isn't really going to work, because as soon as they come down and give you stimulated emission, they go back into level 1 and then they absorb that photon again, so that you're getting no net gain. If you get a stimulated emission being produced with 1 photon, then what you've done is you've increased the number of atoms in level 1, and so you're going to get an equivalent absorption process going on. So 2-level lasers aren't going to work. What we need is to extend the energy level diagram a bit. So we can do that by using a model of 3 levels or 4 energy levels. Ruby is a 3-level laser system, and we'll see a figure of its energy levels here. So we have a ground state, a ground level, let's call that level 1. We have an upper excited state, let's call that level 3, and then we have the upper laser transition line, the upper laser energy level, and we pump the atoms up into this reservoir in level 3. They will fall down into level 2, they will relax down into level 2, and usually this is a non-radiative process. Okay, what do I mean by that? I mean that it's not giving out light, it's giving out heat. It's not giving out laser radiation, it's just giving out wasted energy. And what we would like is, remember what we're trying to do is to get more atoms in level 2 than in level 1. So what we'd like is for them to go up into the reservoir quickly and then fall down and start to fill up level 2 as quickly as possible. Now, we'll need them to hang around in level 2 so we can get enough atoms up and into level 2. So we need them to stay in level 2 for a little while. In other words, the spontaneous emission must be quite weak. And then we get the laser transition going down from level 2 back to level 1. So we want a fast transition for level 3, so there's no point in filling up the reservoir and then the reservoir's full and nothing else is happening. We want to populate the reservoir, the pump band, have it fall down into level 2. We want it to stay in level 2 for a while, and then that gives us a scope for getting lots and lots of stimulated emission and not much spontaneous emission. Okay. So initially all the atoms will be in level 1. The pump excites them into level 3, and from level 3 they go down into level 2 as quickly as possible. and saying that should be a fast radiationless transition, which doesn't emit light. And then finally the atoms fall back down into the ground state and we get our photon emission. So that laser transition is going from 2 to 1 is the one which gives us the laser output. In Ruby, the line width of the upper laser, the pump band, is very broad, and so we can use lots and lots of different wavelengths. We can have a band of about 100 nanometers in the blue and another 100 nanometers in the kind of greeny yellow colour. And these are referred to as absorption bands or pump bands for the laser. And you can use lots and lots of different types of light source: xenon lamps, krypton lamps, mercury lamps, tungsten lamps, and various flash lamps. These are pulsed systems. They give you a big flash of energy, and then we get the laser pulse following. Level 2 is very sharp, very narrowly defined, very narrow line width. So that gives us a narrow range of wavelengths. And for the population inversion, then the amount of time that it spends going from level 3 to 2 must be much faster than the smaller time to go from level 2 to 1. Okay, so the population of level 3, we can ignore it really, because all we want is to use that as a way of getting into level 2. Remember, when we had the 2-level laser, the only way to get into level 2 is via level 1. And what we were saying is that the degeneracy, if we have more routes into level 2 than into level 1, then that will give us a bigger stimulated emission cross-section, a bigger effective target area. So if there's lots and lots and lots of ways, lots of different wavelengths that will take us into energy level 2, and we can only go from level 2 down into level 1, we can't go from 3 into 1, then that means we can start to get these population inversions, and the number of atoms in total is about equal to just the number of atoms in level 2 and 1. And as I say, they don't stay in level 3 for any length of time at all. Now, one of the problems with this is that the ground state is also the lower laser level, so that again means that we have to get at least half of the atoms up into level 2 before we're starting to get gain. Okay, so that's an enormous amount of energy that we need to put in there, and that requires very, very intense light sources. It also means that we can't do it continuously, because if we do it continuously, all that non-radiative transition, in other words, the heat that's being generated as it goes from the pump band down into level 2, won't be dissipated, and the heat will build up in the material. The material changes in temperature will give you a change in physical dimensions, a change in refractive index. Basically, the laser won't work after if there's too much heat accumulating inside the laser material. So that very fact, the fact that we have an inefficient process, if you like, with all the atoms always end up back in level in this ground state, and here we've got heat being generated as a loss, that we need to get half of the atoms, half of the total number of atoms, a huge amount of energy into the system, means that 3-level lasers cannot operate in a continuous wave, so as continuous wave lasers, but they have to work in pulsed mode. Okay, that reduces the amount of power that we need, because we can put everything in one big flash. We can store that energy in capacitors, dump it into a flash tube, give a massive pulse of light in to give us the population into the upper pump bands. And it also reduces the amount of thermal effects, because we're only putting in one pulse and then we're giving it some time in between to relax and cool back down again. So 3-level lasers, not really efficient, but they are sometimes not used very often now. It's usually because you have a specific wavelength that you need to use a 3-level system. 4-level and higher systems are much more common. So the 4-level system, we have our 2 energy levels, energy 1 and energy level 2 again. But this time you'll see that energy level 1 is no longer the ground state. We have an energy level below energy level 1, which is where all the atoms like to sit normally. So that's our kind of ground fill, or where we get the atoms from to pump them up into the pump band. And again, the same thing as we had before. We have a fast transition down into level 2. They'll hang around in level 2 for a while, and we'll get a laser transition, and then they'll end up in level 1. Now, what we don't want is lots and lots and lots of atoms piling up and accumulating with energy level 1. So we need this transition going from level 1 down into level 0 to be very, very fast. Okay. If we have that as the case, then let's take the story of one atom and its photon. So we put in some energy, we take one atom and we move it up into the pump band. Very quickly, it relaxes down into level 2 and it stays there. And now we have one atom in level 2 and no atoms in level 1 yet. So already N2 is bigger than N1. So even for vanishingly small amounts, in theory, the 4-level laser can give us population inversion with much, much smaller amounts of input energy. Okay, so much more efficient than a 3-level system. So again, if we think about the kind of dynamics of this process, we want to go up into level 3, we want that to happen quickly, we want to fall down into level 2 so that things accumulate in level 2. We then want them to give us a laser transition down into level 1, and then we do not want them hanging around in level 1. We need them to go down into level 0 as quickly as possible. The various dotted lines here show you the possible transitions. So you could go from level 3, level 0 to level 3, 3 to 1, that should be. That dotted line should go to level 1, sorry, so ignore that one. Going from level 2 to 0, level 2 to 1, and level 1 to 0. So all of these transitions may or may not be allowed. Typical 4-level systems tend to be solid state systems. So here we have yttrium, aluminium, garnet. So it's a type of garnet crystal. And we can dope it with various rare earth elements. So neodymium, erbium, thaumium, holmium, praseodymium, lutetium, lots and lots of different things that you can put in. And those impurities determine the laser wavelength. The YAG is just the basic crystal. So in the same way that we had pure sapphire with a chromium ion in it, and it was the chromium that was doing all the work for us, the laser work for the ruby. Oops. Then it's the impurity rare earth ions which are doing the work, doing the actual, it's those ions which have these energy levels, and the YAG is basically there just as a matrix to hold those in place. You can use glass as well, you can use all sorts of crystals or glasses. So level 1 doesn't coincide with the ground state. Fantastic, we now have an energy level called E0. We pump from E0 up into level 3, we have radiationless decay into level 2. We then go down into level 1, and then level 1, it falls down into level 0 as quickly as possible. Okay. So in that case, if that's true, those conditions are met, then we have the atoms piling up in level 2 and getting larger and larger population inversion. So CW lasers, continuous wave lasers, are all based on 4-level transitions or higher. For solid state lasers, these the energy which is lost, the non-radiative transitions, are in the terms of the lattice vibrations in the crystal. These are the phonons that we've referred to already. And these phonons correspond to vibrational modes. And phonon transitions tend to be much, much faster than photon transitions. The energy gaps are much smaller, and we can have very fast transitions. So going from level 3 to 2 or level 1 to 0, as long as the gap isn't too big, then these can have very fast transitions. For large energy gaps, if you're going from level 3 into level 1, for example, then that's too much energy for a single mode of vibration of that lattice, that crystal lattice. So going from level 3 to level 1 is not as probable. So we don't have to worry about going from level 3 to 1. And similarly, we don't need to worry about going from level 2 to 0 because it's a big gap, and going from level 2 to 1, that if we had radiationless transitions, then we wouldn't get any light out. So those, if the gap is reasonably large, then we have the need for multiphonon transitions, which are very much less probable than a single phonon transition. And so where we have that as being improbable, then the next probable thing that's going to happen is to give us a photon instead of a phonon. And these photons, the relaxation time, the decay time, tend to be much bigger. So 10 to the minus 3, 10 to the minus 5, compared to the phonons, which are very fast, the radiationless transitions. So graph here showing you some neodymium YAG. So this is Nd3+, yttrium, aluminium, garnet, again, garnet crystal. You can see here's energy level 0, energy level 1, energy level 2, and again we have some pump bands for energy level 3. And what we're seeing here is the absorption as so this is an absorption spectrum of the transitions going from the ground state up into the first band, into the second band, third band, fourth band. So here, 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 and here. So there's lots and lots of different ways in which we can get into that pump band. Lots of different wavelengths that we can use.